These are the notes for Unit 7, Day 8, and they begin on page 22 of your packet. And the focus today is going to be exponential models with differential equations. So this is kind of a unique topic. We've dealt with logarithmic and exponential differential equations in the previous class, but now what we're going to do is we're going to deal with a very specific differential equation that is going to lead to an exponential model. And the nice thing is that there's no calculus involved. I mean, this is for a very specific situation, but we run into this quite frequently on AP tests. So the essential question for today is, how can we recognize when we don't have to do calculus to get a particular solution to a differential equation? So we really want to be able to recognize this because it's a huge time saver. Okay, so in a short description, we call this the law of exponential change. So what we start out with, and we kind of started the unit with this, is when we have the rate of change that is proportional to the amount present. So we're going to look at what's going on here through the lens of this differential equation. So notice my rate of change, my dy dx, is proportional. My proportionality constant is -5, proportional to the amount present. That's what y is. So in other words, when we see this differential equation, the top differential dy, if we see a y here, that's the amount present. So we have a rate of change proportional to the amount present. That is the key to recognize that we don't have to do any calculus. So to see what happens to this information, we actually have to do the calculus once. And then after that, we're just going to watch where the numbers go. So we know that this is separable. First thing we do is multiply both sides by dt. Cancels out on the left. And then because of this form, we have a y that we have to divide out. So we're going to divide out the y or multiply by its reciprocal. It's the same thing. And so we end up with a separable expression that says 1 over y dy equals -5 dt. So if we notice, this should say dt here, not dx. So that was a typo. If you notice, there is no t variable at all, right? Because we have a proportionality constant. We have a rate of change that is proportional to the amount present. And so we integrate both sides. So we know when we integrate 1 over y, or we do the antiderivative, we get the natural log of the absolute value of y. And when we take the antiderivative of -5, we get -5t plus c. And we also know from previous class that to solve for y, we have to exponentiate both sides. So it looks like, oh yeah, we have this initial condition through 0, 4. So we're going to go ahead and plug in 0, 4. So we get natural log of 4 equals -5 times 0 plus c. So we know c is the natural log of 4. So now we can put in 4 right here. So here is our particular expression. Now to solve for y, we know we need to exponentiate both sides. So I'm going to change screens here. This is going to slide up to the top, I think. There we go. We're going to go ahead and exponentiate both sides. Okay. And then we know the left-hand side is just the absolute value of y. And we know the right-hand side we can rewrite as e to the -5t times e to the natural log 4. We know e to the natural log 4 is just 4. And we're going to bring that out front here. So we know that when we drop the absolute value signs, we get a plus or a minus. And we get 4e to the -5t. And then, of course, if this is our initial condition, we would choose the positive solution. So let's take a look then at where we started and what we end up with. So we started with a rate of change that is proportional. There's the proportionality constant. Notice my color coding here. My rate of change is red. My proportionality constant is green, proportional to the amount present. I'm going to code that as blue. Okay, and that's what we started with. Our proportionality constant is -5. Okay, now the other condition is that if we have an initial value that is equal to c, in other words, when t is equal to 0, that's what an initial condition is, initial value is. When t is equal to 0, y is equal to c, then the amount present at any time is an exponential function power of kt. Notice what we have here. Let's reread that. The amount present, y, the amount present at any time is an exponential, e to the power, is an exponential, e to the power, function, and the power is k times t. So look at this power. Remember, k is the proportionality constant, it's -5. So the power is -5 times t for this example. So we can say that in general terms, if we have a rate of change that is proportional to the amount present, that we have, and we have an initial value equal to c, that the amount present at any time, y, is equal to the initial value times the exponential, e to the kt. So this is our solution. So if we look at our solution here, and we follow the numbers, we see that our proportionality constant, -5, goes to the power. And our initial condition, 4, goes out in front. That's our multiplier. And so we should be able to jump from this condition, dy dt equals -5y at 0, 4. We should be able to jump from here all the way to here, the exponential relationship y equals 4e to the -5t, without doing any calculus. Okay, we just know to plot the numbers into the power and out front. Okay, like I said, this is really specific, right? We specifically have this relationship where the rate of change is proportional to the amount present, and we specifically have this initial value of 0, c. Okay, and when we have those two scenarios, we don't need to do calculus. And then just a kind of caveat here, k is the rate constant. If this is positive, greater than 0, it represents growth. If it's negative, it represents decay. Remember those sort of things from algebra 2? Okay, so let's take a look at this then. So here's our relationship from the previous page. Here's our initial condition from the previous page. We know that if we have the initial condition of 0, 4, we have a solution, a particular solution that looks like this. Okay, this is what the College Board focuses on, is this relationship. Con focuses on sometimes not giving you an initial value at t equals 0. And when that happens, we don't get this. We get a slightly modified version of it. So let's go through this just for the benefit of doing your con quickly. So we have to go back then to this general solution, right, before the initial conditions put in. And now we're going to put in our new initial condition, which is not at t equals 0. So that's going to mess up our constant. So natural log of 4, since we have initial condition of 2, 4, we have natural log of 4 equals -5 times 2 plus c. So if we notice, we now have a numeric value here instead of 0. So c is now 10 plus the natural log of 4, because this is -10, and I brought it over to the left side. So we end up having the natural log of y equals -5t plus 10 plus the natural log of 4. And if we exponentiate both sides and rewrite this as e to the -5t plus 10 times e to the natural log 4, natural log 4 will still come out in front, but if you notice, our power is more complex now. So that's what happens when you don't have an initial condition at t equals 0. Okay, so like I mentioned just a second ago, this is kind of the focus on con, is this level of coming up with this particular solution so that we can use it to find values for y, function values. And then this, of course, is a College Board focus where there's totally no calculus involved whatsoever. Okay, So let's look at this. Let's look at a really, really common problem for College Board. So we have to recognize this as a differential equation that we don't need calculus for. So let's look at the kind of the indicators here. So we see the word rate and proportional. So we know to the amount present. So this whole phrase, rate proportional to the amount present, should be screaming this: rate proportional to the amount present. So rate dy dt, proportional k, amount present y. Okay. And then we have time t equals 0. So this is telling us that there's no calculus involved. When t is equal to 0, bacteria is 10 grams. So this is our C value, is 10. So that's telling us that when t equals 0, c equals 10. And so we should be able to write our particular solution. It's going to be y equals, I'm going to stop here. I'm going to have you pause the video and see if you can write the equation without doing any of the calculus. Okay, if you're running the video, you've tried that on your own. So our particular solution is y equals 10e to the kt. We don't know what k is right now. We don't have a number here, a proportionality constant. We have to find that. And that's what we're going to use the second piece of information for. So at time t equals 2, the amount of bacteria in the dish is 30 grams. So when we have 30 grams, we know t is equal to 2. So we're going to put a 2 in here, and we're going to solve for k. So the first thing we do is divide by 10. We get 3 equals e to the 2k, or k times 2. And then we take the natural log of both sides so that we can bring the power down in front. And we have the natural log of 3 equals 2k, right? Because the natural log of e is just 1. Those are those really important values you need to keep track of. So k is equal to the natural log of 3 over 2. So we know that that's what goes right here. So our particular solution is 10e to the natural log of 3 over 2t. I want you to leave that as a fraction with the natural log in here, okay? Because it's going to make your math easier in the end. Notice this is a non-calculator question, so we wouldn't be able to find this decimal anyway. Okay, so now we're going to use the last little bit of information. What amount of bacteria is in the dish at time t equals 4? So if you remember back to the last class, this is what we call a function value question, right? We're being asked to find a function value at time t equals 4, and that's a huge indicator that this is a differential equation problem. Because the only way to find the amount of bacteria present is to get that differential equation integrated if necessary, or at least come up with a particular solution if it's exponential like this. So when t is equal to 4, I'm going to put a 4 in here, and we're going to solve this. So when we put a 4 in here, we can simplify this to be 2 natural log of 3. Okay. And we can also rewrite that. And rewriting this is important because e to the natural log means something, right? So I'm going to rewrite this and bring that 2 up to the power. Because we know that e to the natural log of something, e to the natural log is an identity in that. So we know this whole thing just ends up being 3 squared. So this ends up being 10 times 3 squared, which is 10 times 9, which is 10 times 9, which is 90 grams. So the answer here should be B. Okay, when we get into the classroom then, we'll go over the takeaways, and we'll have you work on some topic questions.